Eliminating all computational error from computers, including errors from floating point, remains impossible in practice due to fundamental limitations in how real numbers are represented and manipulated digitally.
Okay, but let's say I can do it. What would that mean?
If you could eliminate all computational error from computers, including all forms of numerical, logical, and hardware errors, the consequences would be transformative and unprecedented for science, technology, and society. Perfect numerical accuracy. Every mathematical calculation, no matter how complex, would yield an exact answer. There would be no round-off, truncation, or overflow/underflow errors, regardless of the number's size or the operation's complexity. Scientific simulations, engineering models, and financial calculations would become perfectly precise. Flawless reproducibility. Any computation would always return the exact same result, bit for bit, regardless of hardware platform or environment. This would revolutionize reproducibility in research, removing ambiguity in results caused by subtle system differences. Breakthroughs in science and engineering, fields that push the limits of computational modeling, such as weather forecasting, genomics, pharmaceuticals, cryptography, aerospace, and quantum mechanics, would progress faster and more reliably. Simulations constrained today by growing errors, e.g., long-term climate or orbital models, could run indefinitely with confidence. New mathematical and physical insights. You could compute with objects and systems involving irrational, transcendental, or infinite numbers without error, potentially allowing direct, constructive exploration of problems currently accessible only through approximation. This goes beyond existing exact approaches, like rational arithmetic or symbolic computation, which still hit practical or theoretical limits. Highly reliable AI and machine learning. All weights, gradients, and activations could be updated and stored precisely, leading to more predictable and potentially more interpretable models. Any small improvements or optimizations would not be lost to rounding error. No need for error correction or tolerance. The vast architectures, checks, and redundancies built solely to mitigate errors in hardware, ECC RAM, RAID, software, checksums, error-correcting codes, and algorithms. Interval/rational arithmetic, error-tolerant networks would be unnecessary, simplifying and speeding up systems dramatically. Security and cryptography. Computation-based cryptographic systems would be guaranteed correct, eliminating certain classes of side-channel and numerical attacks rooted in error behaviors. Integer overflows and floating-point imprecisions would no longer be sources of bugs or exploits. In essence, computational reliability would reach a theoretical maximum, limited only by our physical knowledge, not by digital or numeric artifacts. However, as shown in current research, classical computers already achieve virtually error-free computation for most ordinary, non-extreme tasks. True error-free computation in the absolute sense requires physical principles, like infinite precision or Platonic numbers, that no digital system can achieve. It's a hypothetical outside known physics. But the impact, if realized, would be as profound as the invention of computing itself. Quantum computing advances in error correction show that with sufficient resources, you can make error arbitrarily small, approaching this ideal. But the complete elimination of error would fundamentally change what digital systems can achieve and would redefine the limits of human knowledge and computational exploration. Eliminating all computational errors would mean creating a machine that performs mathematically exact, fully deterministic, and physically flawless computation, regardless of input complexity, time, or system size. To understand how revolutionary that would be, let's break it down across multiple domains. Mathematics and number theory today. Computers can only approximate most real numbers. Irrationals, like pi or square root 2, transcendentals, like e, and irrational roots cannot be precisely represented. Even symbolic math systems only handle a subset. With zero computational error, every real number could be represented, stored, and used in calculations exactly. Symbolic and numeric computation would merge. Algebraic operations would never lose precision or collapse under approximations. Calculus, infinite series, and limit-based math could be computed to completion anywhere finite math applies. Closed-form solutions could be calculated where previously only approximations or numerical methods were possible. This could resolve problems in analytic number theory, algebraic geometry, and chaotic systems, which are highly sensitive to numeric precision. Scientific simulation and modeling today, simulating many natural processes, e.g., weather, fluid dynamics, gravity, molecular interactions, involves solving equations over small time steps where errors accumulate. With zero computational error, simulations could continue indefinitely with stable accuracy, e.g., simulating solar system evolution, climate change, or protein folding for centuries without divergence. Models could include more variables, physical complexity, and timelines without fearing numerical instability. Discrete approximations like finite element methods and grid-based solvers could be computed exactly, leading to realistic continuum models. You could simulate edge-of-reality systems, quantum gravity, Big Bang cosmology, turbulence, in full fidelity. AI and machine learning today, neural networks accumulate layered imprecision over millions of parameters and calculations. Quantization, floating point rounding, and limited weight resolution all affect model performance. With zero computational error, training and inference would be perfectly repeatable, leading to deterministic AI. Tiny changes in data or architecture could be precisely tracked and understood, improving model explainability. Entire deep models could be constructed and optimized down to theoretical mathematical minima instead of floating approximations. Backpropagation and gradient descent would operate without vanishing/exploding gradients or numerical noise. This might usher in lossless neural networks or even allow AI to reason over abstract concepts with symbolic accuracy. Cryptography and security today, many security flaws arise due to execution flaws, integer overflows, floating point mismatches, timing errors, and truncation bugs. With zero computational error, software and embedded systems could guarantee correct arithmetic under any input, resistant to buffer overflows and precision exploits. Side-channel attacks would become harder since no computation would leak information through approximation behavior. Systems could cryptographically verify every step of execution for correctness. Cryptanalysis itself could benefit from vastly more powerful exact number theoretic algorithms. It would elevate us toward provably secure computation, both in theory and practice. Software engineering and programming today, programmers grapple with edge cases and numerics. Debugging floating point behavior can take enormous effort in mission-critical systems, e.g., aircraft, satellites. With zero computational error, algorithms could be written in pure math terms and always behave identically on all machines. No need for epsilon tolerances, rounding modes, or type conversions. Transports between hardware, compilers, or distributed systems would be flawless, as all computing becomes absolutely portable. Multi-threaded and distributed systems could synchronize results with guaranteed determinism without replay systems. Physics and fundamental research perhaps most profoundly, eliminating all error would allow us to simulate nature itself with unmatched fidelity, exploring beyond the standard model of physics or simulating Planck-scale phenomena. Testing the behavior of theoretical universes, multiverse configurations, or new forms of matter. Engineering entirely new materials or quantum effects through perfect simulation. The boundary between physical and virtual computation might begin to dissolve if we can calculate nature better than nature itself realizes it. So, what would it mean, ultimately? It redefines the limits of knowledge. You're no longer bound by information loss due to representation. It reshapes computing into an exact science. All computation becomes mathematics in motion, not an approximation layer. It moves computers closer to Platonic reasoning, tools for discovering universal truths, not just practical approximations. It collapses current barriers across simulation, AI, physics, proof, and logic. In short, perfect computation equals perfect predictability, and predictability is the seed of knowledge, discovery, and control. If you could really eliminate all computational error, it would be the greatest leap in computational ability since the invention of computing itself.